Hello everyone and welcome to Fusion EP Talks, a student-led webinar platform for sharing knowledge about nuclear fusion, science and engineering. I'm Katerina and today it's my pleasure to introduce you to our Fusion EP program alumni, Alena Gogoleva. Alena has been a doctoral research fellow in the International Doctoral College in Fusion Science and Engineering, Erasmus Mundus Fusion DC program. The research is being done under co-tutel agreement between Carlos III University of Madrid in Spain and University of Ghent in Belgium. In the field of magnetically controlled thermonuclear fusion, her research interests are focused on the characterization of alpha particle transport in the reactor of relevant burning plasmas. And before joining the doctoral program, Alena has received European Master of Science in Nuclear Fusion and Engineering Physics degree by Erasmus Mundus Fusion EP program. And also she has obtained Master in Physics degree, majoring in Physics of Plasma in St. Petersburg State Polytechnical University in Russia. So without further delay, I give the floor to Alena.
Thank you so much, Katerina. Hi, everyone. So let's start. From the title, you may deduce that this talk is dedicated to a problem of alpha particle transport, as their confinement is rudimentary for attaining burning conditions in a future viable fusion reactor. Being born in high energies, alpha particles are not affected by collisions and moving according to a magnetic field only, which may cause drifts if it's not uniform. In the next 30 minutes or so, I'll give you an outlook on the alpha particles confinement by characterizing their transport under reactor conditions and influence of the magnetic field, particularly with toroidal symmetry. I'll start with the basic concept of nuclear fusion, guiding you towards the objectives of this talk. Next, I'll discuss alpha particle statistical description, starting from the equations of motions and the 5 configurations considered, a perfect ether tokamak and 4 quasi-toroidally symmetric accelerators. After presenting the general confinement picture, meaning evaluation of particle losses and their origin, we'll move to the trap particles characterization, as they are the one responsible for transport. As a final part, I'll present the results of the statistical analysis of their trajectories, together with the transport dynamics evaluation, and give you a summary of the key points of this talk. So, nuclear fusion rests on a brilliant and elegant idea of recreating a reaction similar to the one that powers stars under control conditions here on Earth. Future magnetically controlled thermonuclear fusion reactors are planning to use 2 light nuclei, deuterium and tritium, to fuse into a heavier one, producing a neutron and helium-4 or alpha particle. As a result, the kinetic energy will be released due to the mass defect, in accordance with Einstein's famous mass energy equation. The energy of the neutron will be harnessed to initiate the conventional electricity production cycle. Alpha particles, as being charged particles, will be confined by the magnetic field and will be responsible for sustaining the burning conditions. Their loss at such high energies poses a serious threat to the reactor operational control and to its plasma-facing components. Thus, quantitative understanding of alpha particle transport is crucial for a future fusion reactor. Let us consider the basics of magnetic traps. In order to efficiently guide and confine charged particles by the magnetic field, firstly, its lines must be bended into the toroid to avoid losses at the ends, and secondly, the magnetic field should be helical, thus having a toroidal and poloidal components. There are 2 main concepts of how to generate such desired fields. In tokamaks, on the left, the toroidal field coils surround vacuum vessel and generate the toroidal fields, while the plasma itself creates the poloidal component based on the transformer principle. A classical stellarator on the right doesn't rely on plasma to create the poloidal field. For that, besides the toroidal field coils, it has helical or modular shaped coils which create the resulting plasma column being twisted. Tokamaks fields could be considered 2-dimensional, besides the bobbin effect due to the finite number of field coils, while stellarators are truly 3-dimensional. However, such complex geometry could be used as an advantage, since it gives more freedom to optimize the magnetic field structure to reduce particle losses. One of the optimization strategies and to oppose is field symmetry. So we must primarily introduce and adapt it to the toroidal shape coordinate system. One of the most commonly used ones is Boozer coordinate system, where the magnetic field lines are straight. Here, the toroidal magnetic the toroidal magnetic flux is used as radial coordinate. Phi and theta are the toroidal and toroidal angles respectively. Thus, the magnetic fields could be represented as a Fourier decomposition with radial dependence given by BMN coefficients and sine and cosine term containing the angular dependence. For symmetric magnetic fields, the magnetic field strength is a function of the radial coordinate, is just one of the two angular coordinates, or a fixed linear combination of them, giving us three natural types of symmetries: toroidal, poloidal, and helical. In realistic devices, the perfect symmetry is unattainable and can only be approached approximately, quasi. For example, the quasi-toroidally symmetric fields, besides a dominant M0 component, we have other Mn non-zero components. On the counterplot of the field strengths, you could see that there is virtually no toroidal dependence. In this work, we'll consider and concentrate on the toroidal symmetry, which allows to create tokamak-like stellarators with similar confinement properties, the so-called quasi-toroidally symmetric stellarators, and consider both tokamaks and quasi-toroidally symmetric stellarators with different levels of symmetry. Let's consider a single particle motion in a non-uniform magnetic field of a tokamak. Such field divides particles into two types. On the left, the passing particle has sufficient parallel velocity to overcome the magnetic field change and continue to stream along it. On average, it experiences no radial drifts. On the right, the trap particle. Let's see its trajectory. The trap or reflected particle with small parallel velocity is unable to access the regions of high field. It is reflected and changes the direction of motions and remains bouncing back and forth on the outer side of a machine, following the so-called banana orbits. Here you could see its projection, hence the name. The position of the reflection points of these points are highly susceptible to the field corrugations, as field ripples might lead to jittering of the banana tips. Moreover, in a fully three-dimensional stellarator, trap particles may follow way more complex trajectories, as you may see here on the video, and they even could escape. More examples of complex particle trajectories you may see here on the left plot for ripple tokamak and for the stellarator. These examples clearly indicate the key problem of particles confinement. That with the exception of the symmetric magnetic fields, like those of ideal tokamaks, the trap particles do experience non-zero radial average drifts, which might lead to losses even without collisions. There are two main principal transport mechanisms connecting trap particle losses with inhomogeneities of the magnetic field. The first one is ripple trapping. See here the red particle, in which particles fall into local ripples and experience strong radial drifts, usually being convective by nature. The second one is ripple-induced stochastic processes with mild drifts caused by the radial motion of particle reflection points. You could see here on the blue particle. It results either in the banana tip stochastic diffusion, so the jittering, or particle orbit transition near these reflection points. So here we come to the objectives of this talk. While for the particles that circulate in the plasma with the same direction of motion, the passing particles, the absence of net radial drifts is fulfilled per se. For trap particles, that rather than being automatic, it becomes the optimization goal. While the mitigation of collisionless losses is widely considered in the literature on future fusion reactors, far too little attention was paid to the statistical characterization of the processes underlying collision and transport of trap alpha particles. So in this work is intended to provide such description for particle motion in reactor scale configurations in cases of broken toroidal symmetry of the underlying magnetic fields. The collisionless motion of charged particles in magnetized plasma consists of a streaming along the magnetic field lines and a fast duration around it, as we've seen on the videos. With the guidance center approximation, three equations describe it. One equation for the 3D guidance center velocity, one for the variation of the pitch, and one for the variation of the kinetic energy. Here, the drift speed contains three terms, accounting for the fast streaming along the field line, and slow curvature and gradient B drift across it, and the slow drift due to the electric field. However, not all the terms are relevant to describe alpha particles motion. Thus, following approximations were made. First, neglecting the effect of the electric fields, as it would require unrealistic electric fields to make these two drift speeds comparable, which eliminates the following terms. Second, neglecting collisions to highlight the link between the magnetic field, confining, and the alpha particle transport. And finally, we'll consider our alpha particles as monoenergetic, moving with 3.5 megaelectron-volts energy, which vanishes the last equation entirely. When written on Boozer coordinates, the equations of motion reduce to four ordinary differential equations, describing the variation of the three spatial coordinates, psi, theta, and phi, and the pitch. The solution of these equations is obtained numerically with the Monte Carlo orbit following code MOCA, which provides the independent trajectories of alpha particles in given configurations, reassuring that the energy and magnetic moments are conserved. That allows us to statistically analyze their transport based on ensemble average over large sets of trajectories. Thus, here we'll consider 5 reactor scale configurations, a ripple-less ether tokamak, and 4 quasi-toroidally symmetric stellarators, standing for QTS, loosely based on the NCSX project, scale up to ether parameters, meaning the nominal magnetic field of 3.5 Tesla and plasma volume around 900 cubic meters. The 4 quasi-toroidal configurations were generated from the same equilibrium, keeping fixed the few largest modes, starting with 4, resulting in QTS4, and adding on top different number of smaller harmonics, meaning gradually breaking the toroidal symmetry that results in QTS5, QTS6, and up to QTS72. On the upper plot in here, you may see the normalized magnetic field strength along the field line for 3 configurations, ether and the 2 extremes, QTS4 and QTS72. While the field variation is larger for ether, its values are perfectly aligned, as you could see, which is clearly not the case for the QTS configurations. More details of the magnetic field structure and symmetry breaking effect you may see on the bottom plot of the contour levels of the normalized magnetic field magnitude at mid-radius for ether, QTS4, and the most broken one, QTS72 configuration. Thus, as we know which configurations we consider, 5 of them, we will initialize a bunch of alpha particles and follow them in our trajectory, in our configurations. A set of particles for ether comprises of 256 by 256 particles, uniformly distributed in pitch and randomly in poloidal angle. QTS configurations require also a random distribution along the toroidal angle, resulting in a set of 64 by 64 by 64 particles. They were initialized at mid-radius, around the mean alpha particle birth radius, and follow up to 1 second each. No surprise that no particles were lost in perfect ether, while the cumulative loss fraction for the QTS configurations is shown here in the figure. As expected, the higher the symmetry, the longer it takes particles to start leaving, the lower the loss rate, the longer it takes to saturate, and the smaller the loss fraction overall. We classified particles into either passing or trapped, depending on the pitch sign, if it's constant or not, along the trajectory. We found that a third of particles are trapped in ether, and a fifth one for the stellarators, independently on the level of symmetry. However, as the level of symmetry decreases, less and less trapped particles survive. However, all lost particles are trapped, but not all the trapped particles are lost. To better understand the impact of the magnetic configuration and the initial conditions on alpha particle confinement, we present the contour levels of the normalized magnetic field magnitude at half radius for the QTS-72 configuration. It's exactly where we initialize our particles. Here, the mid-toroidal dependence is seen as a signature of the approximate symmetry, and the magnetic field is higher in the outboard and lower in the inboard of the configuration. On the red plot here, we have plotted the particle exit times, average over the initial pitch as a function of the initial poloidal and toroidal angles to highlight this dependence. The plot confirms the weak toroidal dependence and shows higher confinement times for particles born in regions of the higher magnetic fields and vice versa. To further clarify this relation, the escaping times are presented here in the bottom plot as a function either of the initial pitch and poloidal angle or initial pitch and toroidal angle per configuration period. The exit time maps confirm that the most losses belong to alpha particles born with small parallel velocity. Please notice here the clear restriction on the pitch angle and on the outer midplane of the configuration. So, as trap particles are the one that are responsible for transport, the trajectories they follow require detailed consideration. There are a few types of orbits that trap particles could execute. In toroidal geometry, the main ones are banana orbits. Particle trajectory following a banana orbit is reflected 2 times and does not encircle the magnetic axis, crossing the equatorial plane at around 0 poloidal angle. See here the poloidal projection of a blue particle together with the time evolution of its radial position and the pitch. The orbit of a trap particle is called theta, here the magenta line. If it's reflected twice, look at the pitch angle, and does encircle the magnetic axis. Another type is the orbits that change from being trapped to being passing. They're the ones that call transition orbit here in the cyan line. The ripple trapped orbits in red differ from the other 2 types in that they neither encircle the axis nor necessarily cross the equatorial plane in between reflection points. From these orbits, ripple trapped orbits are the most harmful for the confiner as they are doomed to be lost. We performed this classification of the trajectories for all trap particles for our 5 configurations. The reflected orbits are classified for ITER as being 97.3% bananas and a minute percent of potatoes. While for the QTS configurations, 90% were banana orbits and between 2 up to 6% ripple trap orbits with a minute 1% of potatoes. As we could see in our configuration, trap particles mainly follow banana orbits, and we have made an effort to characterize them. The key in the analysis is to notice that every banana orbit is defined by 3 reflection points. In the figure here, one individual banana orbit is drawn in red and labeled by points 1, 2, 3. Let's discuss its characteristic temporal and spatial parameters. The definition of the bouncing time is the time that a particle spends between 2 reflection points, between point 1, 2 or 2, 3. From the mid-radial position and between 2 consecutive sides or orbit sides, in between here and here, it is possible to define the normalized orbit center as a midpoint and the banana width as its difference. For the red banana orbit, the bouncing time was found to be 30 milliseconds and the orbit width 0.22. Thus, every reflected particle trajectory is split into a series of the banana orbits. See here the blue dots, their centers. From the numerical alpha particle trajectories, we will extract and statistically estimate the evolution of the banana centers, banana bouncing times, and normalized banana orbit widths. As a first test, this tool was applied to perfect ITER. 4 sets of around 4,000 particles, alpha particles, born at mid-radius with initial poloidal angles of 0, pi over 4, pi over 2, and 3 pi over 4 are uniformly distributed in pitch between -06 and 06, with an idea to scan the trapped regions. We found that the fraction of reflected particles monotonically decreases with the initial colloidal angle from around 50% at theta equals 0, where magnetic field is the weakest, and up to 18% at theta equal 3 pi over 4, where magnetic field is the strongest. The dependence of the banana width on initial colloidal angle and pitch shows that banana width increases with the absolute pitch. The maximum width is independent on the colloidal angle and extends up to 10% radially, which corresponds to around 30 centimeters for ITER. The bouncing times of most particles is relatively constant, in between 6 up to 10 milliseconds, besides barely trapped particles, which are approaching passing ones. On the lower plot in here, you may see the toroidal projection of some typical banana trajectories left, and of a barely trapped particles that are almost becoming passing. These results help us to anticipate the main spatial and temporal banana orbit characteristics, meaning the most probable value of the banana width for ITER would be around 0.1, and the most probable value of the bouncing time for ITER trapped particles would be in between 6 up to 10 milliseconds. And indeed, now if we will consider all trapped particles in ITER, which is around 30%, and all trapped particles for the QTS configurations, which is around 20%, and we constructed the probability density function for the banana orbit parameters. As we can see, indeed, for ITER, the most probable banana orbit width is around 0.11, and the most probable bouncing time is around 8 milliseconds. For the QTS accelerators, the most probable banana orbit width is almost twice larger. It's around 0.18. And the bouncing time is about 3 times longer. It's in between 20 up to 25 milliseconds. Here, the logarithmic plot of bouncing times reveals that the range of bouncing times for the QTS is broader, though longer times are still way less probable. The other characteristic that we were interested in is orbit displacements, calculated as radial distance traveled from the one center of the banana to another one, either outwards or inwards. While for ITER, they are negligible, confirming the perfect, frozen, repetitive, confined banana orbits. For the QTS configurations, they are quite large and have a complex structure with several slopes corresponding to different spatial scales. That puts into question the locality of the underlying processes. And as the last piece of information we were able to get is an estimate of the motion of the banana orbit centers to evaluate their transport dynamics. To preserve the conservation of probabilities, we analyze only confined reflected alpha particles, meaning for ITER, all of them, 29%, 15% for the QTS4, and only minute 1% for QTS72. The time dependence of the radial PDF of orbit centers, so where the centers of banana orbits are at each time instance, reveals its non-Gaussian shape. As you may see here on the picture, for ITER and the two limiting QTS4 and QTS72. The results for the QTS72 configurations are a bit surprising at first, since they resemble those of ITER. However, the only confined trapped particles in QTS72 must be radially frozen, because otherwise they would be already lost in such asymmetric fields. The middle plot here shows substantial and asymmetric broadening together with a slow outward radial drift for the QTS4. From the slopes of the radial distribution dependence on time by the running moments method, it's possible to estimate the convection velocity as its first moment and the diffusion coefficient as a second moment. The plots here shows the resulting values for the 5 configurations, confirming the presence of transport only for QTS4 and QTS5, as there are still significant amount of trapped particles that's expected to be lost. Let us now compare the results for the transport coefficients, meaning the diffusion coefficient for the QTS4 configuration. One way to estimate it is by using the calculated most probable banana widths and bouncing time. being the characteristic spatial and temporal parameters for trap particle motion. And it's estimated as the width squared divided by the bouncing time, which returns results for the diffusion coefficient being 2 10 to the 4 meters squared per second. The other way to estimate it is by fitting the time dependence of the radial PDF by the running moments, as we just did in the previous slide. That results in the diffusion coefficient being 10 to the minus 2 meters squared per second. The results are clearly inconsistent. This puts into question the classical convection diffusion approach to adequately describe the collisionless trapped alpha particles transport, as the magnetic configuration departs from toroidal symmetry. That highlights the need for the alternative approach, the non-diffusive one. So here I come to the summary of my talk. So I hope in the past 20 minutes I convince you that alpha particle confinement is crucial for a future fusion reactor, that the type of particles giving us troubles and being responsible for transport is trap particles in the absence of collisions, that in configuration and with toroidal symmetry, their trajectories mainly follow banana orbits, as you could see here on the plot. And we developed a technique capable to estimate the fraction of these reflected particles and extract the characteristic spatial and temporal parameters of their orbits from the numerical trajectories. These results show that the statistical characterization of the banana widths, bouncing time, and banana center evolution puts into question the classical convection diffusion approach to adequately describe the collisionless alpha particle transport, as the configuration departs from toroidal symmetry. More about this you could find in our publication from nuclear fusion. These results prompted us to dive deeper and go beyond the diffusion paradigm. In the following study, we showed that the fractional transport theory provides an effective transport model for the system under consideration, revealing that the transport is non-diffusive, being non-Gaussian, non-Markovian, and strongly subdiffusive, meaning that our system exhibits correlations and the absence of definite characteristic scales in space and time, and the presence of memory effects. More about this you might find in our publication in Physics of Plasmas. And that's it. Here I would like to conclude my talk, and if you have any questions, they're welcome.
Thank you very much for the really interesting talk. So now the floor is open for questions. So any questions to Alena? Maybe I've got one. I know you talked a lot about theory and simulations, but I was wondering if you have a way how to compare this to some experimental results, or what kind of diagnostics are used for alpha particles?
So, well, I'm not an expert on the diagnostics for alpha particles. As far as I remember, there are two that are planning to be used. One is the Thomson scattering. So when you inject a laser beam in plasma and see how it scatters, measuring the Doppler shift, and then the debye length also. That's the passive one, and as the active one, I know probably the charge exchange recombination spectroscopy could be used for the detecting alpha particles, for analyzing them, where you inject the beam of particles, and through the excitation of the photons you take the data. However, I'm not sure. I know that they could be used for the energies of alpha particles at around 1.5 millielectron volts, because it's quite difficult to measure anything at such speed as a 3.5 megaelectron volts. But I'm not entirely sure which one will be used, for example, at ITER. Yeah.
I see. Thank you. And we have one question in the chat. I will read it out. So the final result of D is equal 0.01 square meters per second, compared to the typical 1 square meter per second of turbulence means that ultimately ripple effects can be negligible?
Actually, the ripple effects maybe would be negligible for ITER. As you know, there they are planning to there will be 18 toroidal field coils in ITER, and they are planning to use additional coils to mitigate these effects, and to use some coils for the L mitigation to make the magnetic field as smooth as possible. So yeah, perhaps in ITER I was doing some simulation with this ripple configuration for up to 20% of ripple, and alpha particle seems to be quite well confined there. So yeah, maybe for tokamaks, yes, but for the stellarators, however, everything comes to the optimization and to the fight to make the field as symmetric as possible for the symmetric configurations, or overall to reduce or neglect the net radial drifts.
Mm-hmm.
As it done, for example, with the isodynamicity in Wendelstein. So yeah.
Thank you. I hope this answers the questions. Well, in this case, I would like to thank you again for the interesting talk and for joining us.